Hello, Dr. Buzz here. Today I'll be covering part 2 of my linear algebra review for the Math for Computational Chemists playlist. In this video, we'll be covering determinants, matrix inverses, eigenvalues and eigenvectors, and diagonalization. So you can think of a determinant kind of like an absolute value for matrices. You can write the determinant of matrix A as det A, or literally the absolute values in both, and then the matrix A. In a 2x2 case for determinant, in the matrix A equals A, B, C, D, the determinant of A is just AD minus BC. For a 3x3 matrix, you can compute it with A times the determinant of the submatrix EFHI minus B times the determinant of the submatrix DFGI plus C times the determinant of the submatrix DEGH. And notice that for the matrix B, you get a submatrix by crossing off the corresponding row and column that B is in, and then taking the determinant of that matrix. In general, for an n by n matrix, to complete the determinant, it is simply A11 times determinant of M11, where M11 is the submatrix you get by crossing off the corresponding row and column of element A11. And then they alternate signs between as you go across the row. There we go, that's better. Now, matrix inverses. The definition of a matrix inverse is if a matrix B, for given matrix A, if A times a matrix B and B times a matrix A equals the identity matrix, then B is called the inverse of A. And the identity matrix is just the matrix where every element is 0, but every element on a diagonal is 1. And the special property of the identity matrix is that if you multiply it with any matrix, or any matrix with it, it gives you the matrix back. And the important thing to note is that A has an inverse if and only if the determinant of A is non-zero. So for a 2x2 matrix, if you have A equals A, B, C, D, then A inverse is 1 over the determinant of A times D, negative B, negative C, A. And notice that the determinant of A cannot be 0, otherwise this expression is undefined. Alright, now on to my favorite topic in all of linear algebra, eigenvectors and eigenvalues. Eigenvectors and eigenvalues are a crucial part of computational chemistry, and without them, it would be kind of hard to calculate the energy of molecules. But anyways, before I go off on too much of a tangent, eigenvectors and eigenvalues of a matrix A are defined as the set of all vectors V and the corresponding such that A times the vector V gives you some constant times the vector V. And the vector V is called an eigenvector, and the value lambda is called an I don't know if I said that correctly, but the scalar constant lambda is called an eigenvalue, and the vector V is called an eigenvector. And one thing about the eigenvector is that it has to be non-zero, so it cannot be the zero vector. And n by n matrix can have up to n different eigenvectors, each with its own eigenvalue. And the textbook method for finding eigenvectors and eigenvalues is, so you have A times V equals lambda V. That means A times V equals lambda times the identity matrix times V, which is, when you subtract both sides, A minus lambda I times the vector V equals 0. Since we know that eigenvectors can be non-zero, that means A minus lambda I cannot be invertible. Otherwise, V would be the zero vector, which leads to a contradiction. So to find lambda, we must first solve the determinant of lambda A minus lambda I equals 0. And for an n by n matrix, you will end up with a degree n polynomial. However, this is not the way we really do it in real life. There are much better ways of finding eigenvalues than this in real life. And then to find the corresponding eigenvectors, once you have the eigenvalue lambda, you use row reduction to find the set of all vectors that satisfy A minus lambda I for a given lambda. Now we can move on to diagonalization. Diagonalization is a process of finding matrices P and D for a given matrix A, such that A equals PDP inverse, where D is a diagonal matrix. That means all elements on the diagonal can be 0 or non-zero, but everything else has to be 0. If a matrix A is diagonalizable, then that means the matrix P is the vectors V1 all the way to Vn, where V1 and Vn are column vectors, and D is the diagonal matrix with the corresponding eigenvalues. And I realized I made a mistake, so here I should have said eigenvalues and not eigenvectors. And I'll give a short proof of this. If you have A equals PDP inverse, if P is the set of column vectors V1 to Vn written in a matrix form, where V1 all the way to Vn are eigenvectors, then that means that we multiply both sides of that expression by P, you get AP equals P dP inverse times P, and P inverse times P is just the identity matrix, so that'll just be PD. You can show that if P and D are eigenvectors and eigenvalues, then that expression is satisfied. So you have AP equals A times V1 ... Vn. So that means that is the same thing as AV1 ... AVN for each column, which is the same thing as lambda 1 V1 ... lambda n Vn, since V1 are eigenvectors and lambdas are the corresponding eigenvalues. Now that is the same thing as the matrix V1 ... Vn, and then times the diagonal matrix lambda 1 ... lambda n. And notice that is just PD. In the next video, I will cover, if you work in computational chemistry, you never do those by hand. You always use software. So I'll show you how to do those operations with a software called NumPy, which is written in Python. Well, have a great day.